So, very happy today to have Greg Moore, who'll be telling us about topics in the relation of four-manifold invariants and supersymmetric field theory. Thank you.
Okay, thanks. So today I'm going to talk about some old things and some new things. That's the outline. Don't worry, we won't do everything. I hope we get through section 4 here. So let me remind you of the glorious history of the relation of four-dimensional field theory and four-manifold topology, beginning with instantons and the Donaldson invariants, led to the introduction of topological field theory by Witten, which led to the Seiberg-Witten invariants and the revolution of 1995. Although I see the revolutionary junta didn't show up, but that's okay. The main motivation for this talk is the question of whether or not we can learn more about four manifolds using quantum field theory or string theory. And how would you want to generalize the standard Donaldson-Witten, Seiberg-Witten paradigm? Well, there are infinitely many other four-dimensional n equals 2 theories. There are five-dimensional theories. There are six-dimensional theories. And you can couple to background supergravity. So all of those things lead to various interesting four-manifold invariants. Now, why should we do this? Well, one reason is that we might learn more about quantum field theory and the topology of moduli spaces, and as it turned out, even things about analytic number theory along the way. And we can deliver on that promise. That has happened and is continuing to happen. Another thing is you can learn new properties about Donaldson and Seiberg-Witten invariants. We can deliver and have delivered on that promise, and maybe there's more to be said here. Now, the most ambitious and aspirational thing is the hope that we can discover new smooth invariants of four manifolds, which are new in the sense that they're independent of Seiberg-Witten invariants, and we don't know. So the jury has been out on that for 30 years and is still deliberating. So let me say how I want to think about topologically twisted four-dimensional n equals 2 theory. X is going to be what I'll call a standard four-manifold, a four-dimensional, smooth, compact-oriented manifold without boundary. For simplicity, and only for simplicity, it will be connected and simply connected. And on the other hand, an essential assumption in Donaldson and Seiberg-Witten theory is that X admits an almost complex structure, which under these conditions is the same as saying that B2 plus is odd. So automatically we are excluding half the world of four manifolds by some measure. Although interestingly, when you look at these family invariants, you can relax that condition. You do not need to have B2 plus be odd. Now, in Witten's original example, he constructed an SU2 gauge theory whose, quote, partition function is a function on the homology of the four manifold, which only depends on the oriented diffeomorphism type of X and on a, well, it's an SU2 gauge theory, but you can introduce, you can formulate the action with an SO3 gauge bundle with connection. And so it depends on a choice of W2 for that gauge bundle. And that's all it depends on. Now, on the other hand, for other four-dimensional n equals 2 theories, you must choose tangential structures just to define the UV theory. And my favorite example of that is n equals 2 star theory, which is n equals 2 supersymmetric gauge theory, where you add an adjoint hypermultiplet. And just to define the UV theory, you need to choose what I'll call an ultraviolet spin C structure, not to be confused with the spin structures that you encounter when you express the answer in the infrared as a sum over Seiberg-Witten invariants. Those are totally unrelated to this one. So the lesson from n equals 2 stars, in general, you need to choose some tangential structure just to formulate the topological field theory. And so the question is, what can you say about that? And that's a question that I answered with my student Ranveer Singh and Vivek Saxena, postdoc at Rutgers, about a little over a year ago. And we described the topological twisting of arbitrary four-dimensional n equals 2 theories, even those with no Lagrangian. And the key notion there is what we call a transfer of structure group. So if you have a homomorphism of groups, you automatically have a map I'll call phi star from G1 bundles with connection to G2 bundles with connection. Is there any question about that? Most of you, I think, probably understand that pretty well. Okay, so now the other thing I want to use is I want to think about field theory as a representation of geometric Fordism category. So in topological field theory, we say that a topological field theory is a monoidal functor. A d-dimensional topological field theory is a monoidal functor from the Fordism category of D manifolds and lower, equipped with some structure. So I learned from Dan and Mike that the structure should be thought of as a sheaf on man, and for the rest of us, those are just the choices of the background fields. And so that's a functor to vector spaces, the category of vector spaces. And the top examples of the sheaf of on man is the orientations on X or other tangential structures. We want to formulate physical, well, they're all physical. I mean, we want to formulate dynamical theories with correlation functions that depend on metric and so on. So then we have to introduce f of x equals symmetrics. And so then this becomes aspirational. We also want to include principal G bundles with connection and gerbs with connection. And vect then has to be a category of infinite dimensional vector spaces with some structure. And that structure has been discussed by Kontsevich, Siegel, and Vadim. Now, how does this point of view look when you specialize to four-dimensional n equals 2 theories? Well, we'll begin with a Fordism category with background fields F tilde, which are G tilde bundles with connection, where G tilde is this funny group here. Spin 4 will be related to the structure group of the tangent bundle, in the way I'll say precisely in a moment. There's a global symmetry called SU2R symmetry, and the 2 here is the same as 2 in n equals 2 field theory. And then in principle, there can be other background, other global symmetries called flavor symmetries. And I'm not going to pause and give a precise definition of flavor symmetries, just some other factor in your structure group. And so we have a product of 3 groups. And so we have 3 projection operators, P1, P2, and P3, projection maps, P1, P2, and P3. And P1 and P2 and P3 have nothing whatsoever to do with Pontryagin classes. Okay. Spent the morning talking to Dan about P1 structures, and then I just realized, oh my God. All right, so now how is spin 4 related to the structure group of the tangent bundle? Well, we have the obvious projection, and so we require, when we formulate these background fields, we require that this transfer of structure group for the bundle with connection gives us the oriented frame bundle with this Levi-Chebyshev connection. And so therefore P1 star is a spin bundle with spin connection. And so that means that if we try and formulate the theory with this structure group, it's only defined on spin manifolds. But that's not a big deal. We can choose a slightly different set of background fields where we take a finite quotient of G tilde. We quotient by some finite subgroup of the center. And to say that it extends to a larger domain means that our field theory Z, the one we're really interested in, factors through this Z tilde. And so you can do this for suitable C so that you could work with all standard four manifolds. Now I'm not talking about the topologically twisted theory. So let me stress that in a moment. So now I'm going to tell you how to define the topological twisting of such theories. We're twisting in this lecture. There are many ways of thinking about topological twisting. In this lecture, twisting is a special choice of background fields. So it's often said, and I'm sure I've said it myself in the past, that you need, because you have spinners and the n equals 2 super Yang-Millans, that you need to have a spin structure. But upon topological twisting, then you can generalize the twisted theory to non-spin manifolds. And that's the wrong point of view, even though it's very often said. You can formulate the so-called physical theory that depends on the metric on non-spin manifolds if you choose the right structure group. And then, once you've made that choice, then you could describe twisting as a special choice of background field. So it's an important change in viewpoint. Okay, now to describe what twisting is, Witten's original example was based on a simple homomorphism from SO4 to spin 4 times SU2R divided by that subgroup, which is distinguished as the subgroup which acts trivially on the vector multiply. So to describe the homomorphism, we think of spin 4 as SU2 times SU2, and then it just takes this equivalence class to this equivalence class. And the virtue of this homomorphism is that it pulls back spinorial tensor spinorial representations to vector representations of SO4. So for general 4-dimensional n equals 2 theories, the background fields will be determined by transfer from a bundle with connection for a suitable structure group, G twisted. And if you choose the suitable structure group, then the partition function will be locally constant as functions of the connection on the G twisted bundle, in particular, metric independent. So metric independent and independent of the flavor connections. What does suitable mean? Suitable means that G twisted has this structure of spin 4 times C flavor divided by some finite group such that there exists a homomorphism to this G such that this diagram commutes. So here you have the Witten homomorphism. Once you have that, you use transfer structure group with connection to say that we choose a G twisted bundle with connection. That tells me what the background fields are, and then the magic of n equals 2, and in particular the structure of the energy momentum n equals 2 supermultiplet guarantees to you that that the partition function will be independent, not independent, locally constant as a function of the connection on P twisted. Now, because we still have this condition here, the generalization of the spin C connection that we saw in n equals 2 star is basically that we have some kind of generalized spin C connection in the general case. Okay, that's that. So now are there any questions about that?
You say the extra, you spelled what your result was in the example of Lagrangian field here. They map A through G with them.
Oh, yeah, so we described that in detail in our paper. Here I'm stressing you don't see the dynamical fields at all. You know, that's what topological field theory is. It tells you the answer, doesn't it? But we did actually spell it all out in terms of Lagrangian theory. So I'm not going to do it here, it would take too long. But in the paper, it's all looked at. Yeah, including an important condition on characteristic classes. That's a corollary of this point of view. Let's not go there. So I want to review the Donaldson-Witten paradigm. Probably most of you have seen this more than once. So it begins with an odd vector field that squares to 0 on the supermanifold of all fields. And now I am going to start talking about the dynamical fields. So Witten's example was about supersymmetric gauge theory. So now the subscript G means the dynamical fields. So we introduce a principal bundle with connection for the gauge group. And if I denote the local form of the connection as a mu, some local trivialization, then Witten wrote these formulas. So this is really describing an odd supermanifold on the space of fields, and these are just some fields in the theory. A is a connection, phi is an adjoint valued complex scalar, and psi mu are some of the fermions of the theory. And Vallieu and Singer pointed out that these are just the equations of G equivariant cohomology of the space of gauge connections, where G is the group of gauge transformations. This point of view is very important when you generalize to families. So if anybody's interested in the family invariants, come talk to me after the talk. And but I just wanted to mention this. So now you can look at the local observables, which are Q invariant, and since Q of phi is 0, trace of phi squared is gauge invariant Q invariant. there's another odd vector field, a canonically determined odd vector field, so that the graded commutator is the exterior derivative. And that allows you to derive Q invariant observables associated with the homology on the four-manifold. So Witten defined, or should have defined, a function on the homology, which is just the generating function for this these Q invariant observables of the homology. And his main point was that this function on the homology is independent of metric. Now, Witten, and then with important clarifications from Attia and Jeffrey, pointed out that this path integral then localizes to an integral over the instanton moduli space. That's the moduli space of anti-self dual connections. So F plus is F plus RF divided by 2. Now, meanwhile, back at the ranch, Donaldson was thinking about instanton moduli spaces and defined his mu map from the homology of X to the cohomology of instanton moduli space. And he defined a function on the homology of four manifolds by integrating e to the mu over instanton moduli space, and showed, surmounting a lot of technicalities, but showed that even though the instanton moduli space depends on the metric, this function does not. So the main statement is that these functions on homology are equal, so I'll call it the Donaldson-Witten partition function. So that's all well and good. So that's 1988. Now, how do you actually go about evaluating this in an effective way? Well, from the physical point of view, you start with the idea that this is independent of metric. So it's independent of scaling up the metric. So you could use low energy effective theory, which was worked out mostly by Seiberg and Witten. And from that point of view, you see that the partition function in the infrared point of view is a function of two terms called the Coulomb branch term and the Seiberg-Witten term. And I said it's metric independent. It's formally metric independent. It's metric independent up to a total derivative on field space. So these path integrals are integrals over field space. The metric dependence is a total derivative on field space. There could be a boundary term from a total derivative. And careful evaluation of that total derivative shows that actually there is metric dependence. That's what the superscript J means. But the metric dependence only shows up when B2 plus is 1, and it only depends on the metric through the choice of an oriented line through H2 plus sitting inside H2x. Okay, now the crucial thing is that you can derive the Seiberg-Witten contribution from the Coulomb branch contribution. You do that by determining a bunch of universal functions, and that reminds, I mean, in the hands of Gocha Nakajima and Yoshioka, they had a similar, they had some story like this where they relied on Mochizuki's work. So making a clear connection between Mochizuki's universal functions and the way the physicists derive it is something that really could be clarified and would be nice to clarify. Anyway, continuing with the physical approach, because you can derive the Seiberg-Witten contribution from the Coulomb branch contribution, I'll indicate in a moment how, it's good to start with the Coulomb branch contribution. And what is that? That's an integral over the Coulomb branch, and for rank 1 gauge groups, the Coulomb branch is just the complex plane, famously parameterized by U, where physically U would be thought of as the expectation value of this operator based on square. Okay, so now you can compute the Coulomb branch integral using the low energy effective theory of Seiberg-Witten together with couplings to background gravity and flavor gauge fields, which were not determined in Seiberg and Witten and must be determined in other ways. Now, the complex plane, well, that's a genus 0 surface. And it turns out that it's nice to parameterize it as the a modular surface for the congruent subgroup gamma naught 4 of the modular group. And when you do that, then the integral becomes an integral over this modular curve of a holomorphic function of tau and a total derivative with respect to tau bar of some other function, which for the physicists in the room comes from the photon path integral for the low energy U1 gauge field. Now this thing, this G hat, depends continuously on the metric. So that doesn't look very good for the almost metric independence here, but amazingly, when you do this integral, it only depends on the on this line, oriented line in H2 of X. H and G hat of J only depend on the topology of X cohomology ring. And something we didn't understand until a few years ago is that this G hat is what's called a mock Jacobi form. So here's where the analytic number theory comes in. And we actually learn things about analytic number theory by trying to understand these integrals. Okay, well, it's a total derivative of things with modular properties, so you could do the integration by parts, and so you end up with a contribution from the three cusps on the modular curve. The cusp at infinity, which turns out to match everything we expected from Donaldson theory, and then contributions from the cusp at tau equals 0 and 2, which correspond to u equals plus and minus lambda squared, which give contributions that are not seen in Donaldson theory. And what's going on there is that the singularities there spoil topological invariance, but at these points on the U-plane, at plus and minus lambda squared, the Seiberg-Witten theory is breaking down. It's not a valid effective theory, and you have to replace it by another effective theory, valid in the germ around these points. And that effective theory has both a U1 vector multiplet together with a hypermultiplet, which is called in the mathematical literature the monopole field. So, so we have to add in another path integral for the appropriate effective theory valued at these 2 points. So I'll call that S Z sub Seiberg-Witten plus or minus lambda squared. And the value of that path integral is a sum over C structures. Those are basically the fluxes of your low energy U1 gauge field valid here. The Seiberg-Witten invariant times some function of the homology class. And that function is computed by canceling the metric dependence from the Coulomb branch. And that's the derivation of the Witten conjecture. So yay. Okay, so that's the derivation. Now, but that was only for SU2 super Yang-Mills with no extra fields. And so the question is, one question is, what about the infinite collection of other n equals 2 theories, all of which can be topologically twisted, even those without Lagrangians? So what can we say about those? Well, first of all, we should ask, what do these other Lagrangian theories do? And at least in the case of the Lagrangian theories, we know that they're integration of cohomology classes on a space M, which is the moduli stack of non-abelian monopole equations. So that was again pointed out 30 years ago. So instant-time moduli space is a very special case of all this. So what are these non-abelian monopole equations? Well, now this is Hassan's question is relevant here. Now I'm changing G twisted to include the dynamical fields. So if you do that story from the beginning, including the dynamical fields, you're looking at this kind of structure group divided by a suitable finite subgroup. Again, the projection on this factor is fixed. So we're basically getting a spin seat connection there. And the matter fields, well, for the experts, the matter fields are in the quaternionic representation of the gauge group. For simplicity, I'll assume my quaternionic representation is a V plus V star, where V is a complex representation of the G tilde. And V must be such that V tensor, the chiral spin representation of spin 4, is actually a representation of this G twisted. Under those conditions, if I have a principal G twisted bundle, then I automatically have an associated bundle, and that's my monopole field. And so then the non-abelian Seiberg-Witten equations are self-dual field strength of the dynamical gauge field is there's a standard way of taking M and M bar and combining it into an adjoint valued self-dual two form where I've read all the indices out. Then you have the Dirac operator on there. So those are the Q fixed point equations for this theory with hypermultiplets. Now I want to stress that I'm calling these the non-abelian monopole equations. I should not call them the non-abelian Seiberg-Witten equations because that's misleading. The Seiberg-Witten equations are equations for spin C structure. These are these are connections for the non-abelian gauge field. The spin C connection and the flavor connection are fixed background fields. Okay, so that's what I just said. Okay, so now this brings us to an important point. I said, what is the path integral computing? It's computing intersection of cohomology classes on this non-abelian monopole moduli space. Well, that means you need to orient it to integrate the moduli space. So in 4 dimensions, you need to know something about W1 of M. Now, looking ahead, in 5 dimensions, you need a spin structure, or at least a spin C structure. So you need to know about W2 of M. When you get to 6 dimensions, you're going to be starting to do elliptic cohomology, so you need to know something about P1 of M. So thus, as far as I know, we don't know too much about that. However, in discussions with Dan and Mike Hopkins, we did settle the case of W1 and W2 for the instanton moduli space with very special case. And there's a nice theorem for the instanton moduli space. There's a KO class on connections mod gauge transformations, which restricts to the tangent bundle on the instanton moduli stack. So this is what the K-theoretic KO class that you get from the Tia Hitchin-Singer complex. And the draft, there's a more or less complete draft. It computes the first and second Stiefel-Whitney classes for T. And there's kind of a big surprise, at least for me, which is that they turn out to be cohomological formulas in terms of the Stiefel-Whitney classes of the tangent bundle of X and of the gauge grub. And that's a surprise. Why is that a surprise? Because WIOT should be formulated in terms of mod 2 indices. And in general, mod 2 indices are not cohomological, but here they are.
You need hypotheses.
Pardon?
You need hypotheses for that.
Okay. Remind me later what the hypotheses are. So here's just to show you that there are formulas. Here are the formulas for W1 of T and W2 of T, and I'm not going to go through all the notation. But yeah, I should say, yeah, my role in this project has been a little bit like that of Edmund Halley in the writing of the Principia. So the Principia would not have been written by Newton if Edmund Halley had not been around. So I have been, both cheerleader and pest, and so and that's been my role. But at least I managed to get this far with them. Okay, so we do have something known about W1 and W2 for instanton moduli space. We would really like to know about W1, W2, and P1 for the non-abelian monopole moduli spaces. So that's open. Now, that's what the Lagrangian theories compute. What do the other Lagrangian theories compute? Well, we don't know. For the non-Lagrangian theories, there's no known description of the intersection theory on some moduli space of solutions of some PDE. We don't have some fundamental set of fields, say in the 60-20 theory, for example, or class S theories. And it's unlikely that there is such a description. Now, remarkably, we can still say what the answers are. So this is a funny situation where we know the answer, but we don't know the question we're answering. So in the Lagrangian cases, we know what we're answering. We're looking at intersection theory on non-abelian monopole moduli space. In the non-Lagrangian theories, we don't know. what we're answering, but here's an example of what the answer looks like. So basically the simplest four-dimensional non-Lagrangian theory is known as the Argyres-Douglas theory. So you can write the formulas when not assuming that X is of Seiberg-Witten simple type. But if you assume that it's a Seiberg-Witten simple type and B2 plus is bigger than 1, you have a fairly simple formula. It's not an infinite series in the homology classes, the way Donaldson invariants are, but it's just a polynomial. And it's a very explicit polynomial. So this coefficient B is made out of the Euler character in the signature. And kind of a surprise is that P drops out. So U of P is a null vector, if you like. But it turns out it's not a null vector if you do not assume that X is of Seiberg-Witten simple type. So when I wrote this paper with Yuri Dadaev, well, the way our take on it was, well, if you can't give me a good physical reason why this should be a null vector, then there ought to be manifolds which are not of Seiberg-Witten simple type. But we don't. Okay, so that was the simplest non-Lagrangian theory. Are all the invariants for non-Lagrangian theories expressed in terms of Seiberg-Witten invariants? Again, we don't know.
How you're approaching,
Pardon?
what's the definition?
Thank you. That's really subtle. So Yuri and I had to work very hard on that. So you need to look at, so first of all, you know the infrared theory, because near the Argyres-Douglas point, you know the family of Seiberg-Witten curves. But then you have to study the behavior near the Argyres-Douglas singularity and try and separate out the degrees, the contribution from the degrees of freedom of the Lagrangian part. And we have a procedure explicitly, a very careful limiting procedure where we separate out, we take some limit of shrinking disk and you have to subtract off some stuff, which we claim is subtracting off the local, the theories, the degrees of freedom with Lagrangian description. And we said the remainder has to be the Argyres-Douglas part. So we did a very explicit, concrete prescription. And, doing that for the other non-Lagrangian theories is not something that's been done. It's an interesting question.
So this is only for the SU3 Argyres-Douglas. That's the 3 and
This is for the very simplest, right, the simplest.
but for no other class S.
As far as Elias has thought about this. Elias, for coming to work with him soon, but he's thought about this for other theories. But as far as I know, he hasn't done a very careful limiting procedure the way Yuri and I have did. Okay, so for what it's worth, in a paper with Jan Menska, we made some relevant remarks hinting that the answer is, or at least for class S theories, if you do something similar, it'll always be expressed in terms of Seiberg-Witten invariants. So, but there are lots of holes in that argument. It really is worth investigating it further. Okay, so let me come. How am I doing for time? Not too good.
Are you like 25 more minutes?
Yeah,
We started late.
Okay, so massive surprise from super QCD, by which I mean, if you look at the mass dependence carefully, something interesting happens. Okay. That's work with Elias Furr, postdoc at Rutgers, and Jan Manska. And so what do I mean by super QCD? Well, from the point of view of this talk, in terms of the dynamical fields, our structure group is SU2 gauge theory, spin 4, and there is a global symmetry, which, because we're going to be working with generic masses, is just U1 to F. F is the number of quark flavors, and because of pesky constraints like ultraviolet, requiring ultraviolet fixed point, ultraviolet completeness, and the beta function, F has to be between 1 and 4. So what is the matter? How are we going to describe the matter? Well, we're just talking about the non-abelian monopole equation. So let E be the fundamental representation of SU2. So the C is such that E tensor S plus is a representation of this group. We have F copies of that. And so here we have the non-abelian monopole equations written out with all their indices. I couldn't get PowerPoint to do a Feynman D slash, so D is just is the Dirac operator, capital D. Okay, so this is our moduli space. Now this moduli space, everybody sees, sees these equations as yeah. But this moduli space is kind of weird. Fian and Linnes have spent decades studying it for the case of F equals 1. For the instanton moduli space, we have this famous formula, and then it's a theorem that if you look at a generic point with generic metric, it's a nice smooth manifold of that dimension. But the index of the Dirac operator has the wrong sign. So we really have to talk about the virtual dimension, which looks like this. And so what we have is we definitely have an obstruction bundle. And that's going to cause headaches. So the non-abelian monopole equations have a U1 to the F global symmetry where we rotate each of the monopole fields by an independent phase, and we work equivariantly with respect to the mass parameters. So physically, these are the masses of the various quark hypermultiplets. Mathematically, they're equivariant parameters for working with the U1 to the F global symmetry.
Is there a simplification for, I'm asking over because I see the 4 minus F.
Well, yeah, right. So of course, F equals 4 is super important, right? That's a superconformal theory. And it's not an accident that the K drops out.
Yeah.
And if you look at the N equals 2 star theory, also the K dependence drops out.
Mhm.
And I know what that means in the N equals 2 star theory. It means that you have modular functions as a function of Q. And so here there's an ultraviolet coupling, and again, all instanton numbers are going to contribute. You're going to see something interesting about polynomials in the case. Okay, so if you just follow the Atiyah, Matai, Quillen, Atiyah, Jeffrey story for what the path integral is computing, then you're going to be led to a formula like this, which should be taken with a big grain of salt, as you'll soon see from the answers. Now, one thing we can say for sure is that, let's see, here's our non-abelian monopole equations. F plus of the dynamical gauge field is a sum of M bar J, and then we have D slash of Mj. So now if we localize with respect to these symmetries, Mj goes to phase times Mj. Well, there's one obvious branch, which is where the fixed points, where the Mj is 0. And so then we just get the instanton equations. Okay, but then there's another branch where Mj is not 0, and then the gauge bundle is reducible. So I'll call it the instanton and reducible branches. And so correspondingly, if since you think we can apply the U1 Atiyah, Bott, Berlin, Invariant fixed point formula to this integral, we expect an expression that looks like that. Now, long ago, Losov, Nekrasov, and Shadashvili gave us pretty good understanding of what this should be, computing. So I'm making more precise what I said before about intersection numbers of cohomology classes on moduli space. In this case, you have a sum over all instanton numbers. There's a parameter in these theories called the dynamical scale parameter raised to the virtual dimension of the non-abelian monopole moduli space. You have a product over the masses raised to the index of the Dirac operator, integral over instanton moduli space, then a product over the flavors of a sum of the Chern class of the index bundle of the Dirac operator over the power class. So that's what we plan to be computing on the instanton branch. Much less clear what's going on here. Nevertheless, this is again an example where even though we don't fully understand, I mean, this is some complicated singular stack. God knows what this integral really means. But again, we can use physics to say what the answer is. So because Seiberg and Witten gave us the Seiberg-Witten special Kähler geometry for these theories back in '94, and in part it's based on a family of elliptic curves, and those elliptic curves can be put into Weierstrass form. So G2 and G3 here are polynomials in the scale, the masses, the U parameter, and this is for f equals 1, 2, and 3. It can also be written for f equals 4, then instead of the scale lambda f, you have modular functions. Here's some examples of, here's some examples of the polynomials for f equals 1, for n equals 2. You see they're polynomials as advertised. So what you get is you get a family of elliptic curves over the U-plane, which degenerates with I1 singularities at f plus 2 distinct points. And what are those points? Those points are where the discriminant of the elliptic curve vanishes. So it's very explicitly this polynomial equation that you, where f plus 2 roots of that. So here's the picture. Generically on the U-plane, you have a nice elliptic curve. You have one period goes to 0, the other period is not 0. F plus 2 minus Uj. Okay, now in my paper with Witten from 97, we actually gave a formula for the Seiberg-Witten contributions for any family of Seiberg-Witten well, any special Kähler geometry really for B2 plus bigger than 1. If we specialize that to the present case, and we don't, just for simplicity, I'm not inserting any observables, no two observables, no point observables. I'm just studying the partition function as a function of the masses. We'll have our hands full with that. So it factors as a product of two terms here. One is a sum over spin C structures of the Seiberg-Witten invariants weighted by a sign. And the other is a contribution from each of these singularities on the U-plane. So it's a sign, a power of 2, a power of 3, the C1 squared and chi h. Yeah, I should write those. C1 squared is equal to 2 chi plus 3 sigma. Chi is Euler character, sigma is signature, and chi h is chi plus sigma over 4. So it's just a way of packaging the Euler character and the signature. Power of the scale, and then this rather complicated expression. So you have to solve those algebraic equations, then you have the roots, you plug those in to these Weierstrass invariants. You also have to divide by delta prime to the chi j, where delta is the so-called physical discriminant, not exactly the mathematical discriminant of the elliptic curve. It's just the product of u minus j. Okay, so that's pretty much where it was in 97. Now, Elias, working very hard, looking at hundreds of examples with Mathematica, found that if you actually sum up over the singularities, the result is astonishingly simple. If you look at what we're summing, this is actually what I'm showing you up here. It is simple. Okay, like, oh, it looks simple to you, but it's simple. See here, this is the result of the sum over singularity. So this is the result of the path integral as a function of the masses for these SQCD. Okay, and you know, this is supposed to be the integral over non-abelian manifold moduli space. Okay, of some kind of Euler character, some obstruction function.
This is experimental, I believe.
This is experimental. We're doing experimental physics experiments. Yes. C here is a sign, positive power of 2, some power of scale. And V, P, and Q are relatively prime polynomials in the masses and the scale. Okay, V we can dispense with rather easily. V is just a van der Monde in the masses. Simple. What is P? Let's have a look at this polynomial P in the denominator here. Well, so I said we have this physical discriminant, which is some polynomial in U. So now you can take the discriminant of U, discriminant of delta as a function of U, and that's going to be the places where places where the low energy effective theory becomes more singular. And so So anyway, it factors as a product of a polynomial to the third power times the Vandermonde of the masses. That's already rather surprising. And this PSC is the minimal polynomial of the locus where your Seiberg-Witten curve can degenerate to a cusp, y squared equals x cubed. So it's those that locus of masses and scale such that you can have this cusp singularity in the Seiberg-Witten curve, and that was interpreted particularly by Arger's, Plesser, Seiberg, and Witten, following Arger's and Douglas, as places where you could have superconformal theories. And so we know these polynomials very explicitly here in the first two. Now I'll say more about this P in a moment. What about Q? So Q is a relatively prime polynomial in the masses and the lambdas, and rather strikingly, it has integer coefficients. And if you look at the expressions if you look at the way we got it, it's not at all obvious that it will have integral coefficients. Overall, I had just a positive power of 2. You might have expected, the best you might have expected is some rational polynomials, so you could pull out the least common multiple of all the denominators, but no, it's just a positive power of 2 times a polynomial with integral coefficients. So it's just screaming for some mathematical significance, which we do not know at the moment. But this is all very, very new. And so we've just realized that, gosh, there's this polynomial with integral coefficients. So that's an interesting experimental discovery. Just for laughs, we have reams and reams of data generated by Elias. And, this is an example with one flavor, chi-h equals 2, and various values of C1 squared. Okay, so back to this formula. So there's another funny thing about this formula. You notice that this polynomial, which is 0 when you have superconformal theories, only turns on when chi-h minus C1 squared is sufficiently positive, specifically because of 3. So, but physically, there should not be any singularity here, because for f equals 1, the field space is compact. There's no non-compact field space. There's no room physically for a singularity in the partition function. So therefore, we must have the sum over the Seiberg-Witten invariants be vanishing for chi-h minus C1 squared bigger than 3. And so this is the picture. So if you plot four manifolds as a function of chi-h and C1 squared, then below this line, you have to have the sum of the Seiberg-Witten invariants equals 0. And that's a special case, in fact, of what are called the superconformal sum rules, which I pointed out with Marcos Marino and Grigor Perazza, using essentially the same argument. And I believe that those have been rigorously proven. I guess assuming Seiberg-Witten simple type. Anyway, let's our answer, our final answer then is for the partition function is this. So there's still some interesting comments to make about this answer. First of all, you can look at the large mass limit. When all the quark masses are much bigger in absolute value than the scale of the theory. And in that case, then the f plus 2 singularities on the U-plane split into 2 groups. There's a group near the monopole and Dion singularities of the NF equals 0 theory. And then there's a group of singularities which are mj squared plus some contributions which are vanishing in large mass. So by the way, that formula for the discriminant is really remarkable because notice that they're not exactly mj squared. So that discriminant of delta of u should be uj minus ui. And so the fact that the Vandermonde in the mass is factored out is just extraordinary. Anyway, so therefore it makes sense to write to decompose our partition function as a sum of 2 terms. One from these 2 points, the sort of the monopole and Dion points for the NF equals 0 theory, and the other points. So here's an interesting conjecture. So the U1 to the F localization, I said, splits into an instanton part and a reducible part. And in the large mass limit, we also have this kind of decomposition. And so the conjecture is that the instanton part, for which there's this very explicit formula in terms of intersection numbers of the current classes of the index bundle of the Dirac operator, an instanton moduli space. So this we have a good ultraviolet understanding with. Should be something just the sum of these two contributions. And those we know very explicitly from that formula in terms of the values of the Weierstrass parameters on the roots of the UJ. So in a paper on S duality of n equals 2 star, Jan and I saw some glimmerings of this. But recently, in a separate work, Elias Führer and Jan Manscott have verified this conjecture in a highly non-trivial way by reproducing intricate formula of Goethe and Kuhl on the gray numbers of moduli spaces of sheaves of algebraic surfaces. So these are really complicated numbers, and they just, everything is bang on. So really nice. So that's very strong evidence in favor of that conjecture. Now, what can we say about the singularities when V of m equals 0? Well, what's happening here is that mass parameters are mi is equal to mj, which means that mutually local singularities on the U plane are colliding. So the picture is like this. We have our monopole and dion points, and far apart, we have these mutually local singularities of mutually local massless, nearly massless monopoles coming together. So we have several light monopole fields, and so we should, in the low energy effective theory, which is valued in a region around this point here, the Q fixed point equations should be a generalization of the Seiberg-Witten equations called the multi-monopole equations. And these equations have been studied a little bit in the mathematical literature. These are equations for spin C connection. And they have a moduli space, but you see the Seiberg-Witten moduli space is famously compact, and typically a finite union of points. And so the Seiberg-Witten invariant is a signed sum over that finite set of points.
Is there a Dirac operator? Is there a Dirac equation?
Yeah, I left it off. Yes, each of these sets has the Dirac equation. Yeah. When f is bigger than 1, then the moduli space of this is non-compact, but you can use these equivariant parameters to define a convergent integral, and that equivariant integral indeed vanishes like some power of the van der Waals. It's pointed out by Denishenko, Kukov, and Putrov. We have a formula that looks like 1 over the product of mi squared minus fj squared with a tau h. Well, they wanted to say this looks like vertex operator correlation functions. For us, there's this Q up here, which is non-trivial. Okay, so I'm probably out of time.
No, 5 minutes. Keep going. 6 minutes.
Keep going. Okay. Let me do the 3-slide summary of everything that remains. Then it's audience choice. What doesn't really hear anymore. What's in the rest of the talk? Well, okay, you can go on to 5 dimensions. And you can look at 5D super Yang-Mills theory on a product of a 4-manifold in a circle. And it's topological on X, but not on the circle, so it depends on the radius of the circle. And the partition function is then a series in the radius of the circle. The powers of the radius are the instanton moduli space dimension divided by 2 times ik, where ik is the L2 index of the Dirac operator on instanton moduli space. But wait, you said, instanton moduli space is not always spin. I showed you the formula from Dan and Mike for the non-trivial W2. So what are you talking about? Well, so there's an interesting anomaly cancellation story. So if you look at the action for the 5D super Yang-Mills theory, there's a term in the super Yang-Mills theory, there's a conserved current, namely trace of F, which F calls the instanton number current. And the particles that are charged under, so there's a global U1 I symptom. For example, instanton particles in the 5D super Yang-Mills theory are charged under this one symmetric. And so the 5D super Yang-Mills action coupled to a background one I bundle with connection with I as a term. It's better to write this in terms of differential cohomology, but that's part of the story in the slides. So it looks a little like this. And this turns out to be not quite well defined. On the other hand, there's a global anomaly in the 5D fermions in 5-dimensional super Yang-Mills. And the product of this and the Pfaffian of those determinants is well defined. But you have to turn this on. So this U1 line bundle, let's call it Li as a first term class, and that's what I'm calling N. And there's an anomaly cancellation condition, but basically you have to turn on N in order to fix the fact that instanton moduli space is not in general spinnable. Once you do that, we conjecture that there's a spin C structure on instanton moduli space. And this is the L2 index here of a spin C Dirac operator. Now, again, using these kinds of Coulomb branch techniques, you can evaluate this series quite explicitly. And interestingly, there's a singularity when R to the 4th equals 1. And R to the 4th equals 1 is where there are 5-dimensional superconformal theories. And if you look at the singularities and you try and run this argument that the topological invariance should be fixed by some contribution from the Seiberg-Witten type invariance, it doesn't actually work for the standard Seiberg-Witten invariance. So it suggests that there's some kind of generalization of Seiberg-Witten invariance.
Can you say which four superconformal
Pardon? Which four?
So there are sorry, which superconformal theories do you get that are
Well,
with? I mean,
I think it's called the E1.
yeah, exactly.
E1 theory.
Okay, and that appears at all values.
I think that's the one that appears. Yeah, there's also an E1 tilde.
I guess there's not enough matter here to get the other ones.
Yes, there's
okay.
not a yes. There's an E1 and an E1 tilde.
Yeah.
I think we're getting the E1, and we had reasons why we didn't get E1 tilde. And I think we get E1 at all four singularities.
You mean the generalization of Seiberg-Witten invariance in 4D or 5D?
40. So again, it has to do with these multi-manifold equations.
But there should be a 5D PDE too, right?
Not really, because we're only topological on X, and so we're really doing we're really studying a four-dimensional Kaluza-Klein reduced theory. So we're using a whole apparatus of 4D n equals 2 theory with a prepotential, extremely complicated prepotential calculated from Nekrasov partition function.
Yeah.
So on.
Can you dispense with the condition on V2 plus?
Pardon?
Okay. Can you dispense with the condition on V2 plus?
Not here. We still need V2 plus.
Because an index of a Dirac operator should be a cobordism invariance, and that kind of makes you think that if you go through a wall crossing, maybe that's the sort of thing that remains in. So maybe you have an invariant for manifold V2 plus equals 1, which would be very nice. I'm just.
I'll think about that some more, but I believe that we still need V2 plus. Sorry.
Because if you had invariants that could detect fake CP2s, that would be big for topology.
Could detect
Could detect fake CP2s or fake
Oh, yeah. That
forces,
would be great.
that would be big for topology. So
Yeah.
when I was reading your paper. Anyway,
But it's even worse now, right? Because if it's multi-manifold modular space, like it's non-compact, so it's a cobordism of, it's non-compact.
Yeah,
Matrix.
so,
It's
I
not-
mean, we don't understand. I could show you the slides with some more details, but this is a summary of what's in the remaining 2,000 slides. But, yeah, I mean, we understand that there's a integral, an equivariant integral of abelian multi-manifold moduli space that diverges. But we speculate, and a similar speculation appeared in a paper with Elias and Aspen and Manscott when they studied super QCD, that there's some generalization of Seiberg-Witten invariants, but we do not know how to. That will fix up the topological invariants for these superconformal theories, so these 5D superconformal theories. But we do not know how to define it in a mathematically respectable way. It's just that the formulas are suggesting that there should be such a thing. Okay, you can go on to 6 dimensions. We haven't done as much work on that. I mean, for 5 dimensions, we spelled out like every possible detail. For 6 dimensions, we're expecting, again, a series like this, but now we're looking at the elliptic genera of non-abelian manifold modular space. Interestingly, you need to use non-abelian. You can't use instanton moduli space. And why is that? Because 6-dimensional super Yang-Mills is anomalous. It's not a good it's not a good field theory to do the path integral over. You must introduce hypermultiplets to cancel the gauge interval. So there's no way, Dan, you can get away from non-abelian manifold moduli space. So, got it? Okay. Family invariants. So last part of the talk, that's work with Vivek Saxena and Martin Rocek and Jay Cushing. Is you can couple these 4-dimensional. Okay, so you can couple these 4-dimensional n equals 2 twisted super Yang-Mills theories to supergravity, after all. But we want to work in the world of topological field theory. So pretty non-trivial thing is that there's a consistent way to truncate and topologically twist superconformal gravity. And you end up just describing the equations of equivariant cohomology for the group of oriented diffeomorphisms of X. And so you get equations that look like this. You have a metric, you have its fermionic partner, and you also must introduce a vector field. And so then these are background fields. We're not integrating, we're not attempting to do supergravity. We're not attempting to integrate over the dynamical gauge field, dynamical metric. We are integrating over the dynamical gauge field. So our path integral becomes a function of the metric, the fermion, and the vector field. And we argued in our paper that these should be representing, really following this Bellingcat-Singer point of view. We argued in our paper that these should represent interesting cohomology classes in the classifying space for the oriented diffeomorphisms of X. And so there's a massive paper that we wrote about 2 years ago that does that. Okay. So, yep.
Thank you for the talk. That was a really good question.
Yeah.
Is the paper with the sequent classes with this time moduli space available for them?
I don't think so.
Okay.
So is that right, Dan?
There's a third author.
There's a third author who's not doing anything. So we would want to make it available. So yeah.
Can you go back to this slide where you mentioned a conjecture that had to do with the population of the labor class? So you
Oh, yeah, sure. Yeah, that paper isn't out yet, but it's about, I mean, they have a complete draft. Here it is.
So I have 2 questions. First, what is this D red?
What is Z-red?
Yes.
Z-red is the thing we calculated from the Coulomb branch integral. And to be, I mean, this is really, really concrete. I'll show you what it is. Let's see, where did I? Here it is. Z red is Z pink. Okay, so it's this sum of Seiberg-Witten classes, and then this very explicit expression where now you say which QJ am I? So these are the Weierstrass invariants in the Seiberg-Witten curve. Which UJ do you use? Well, the point is that you only can do this when you're in this limit. And in this limit, two of the F plus two singularities become distinguished. So it's, let's see, I have a picture. There's the picture. So it's these guys down here in the large mass limit. And so those, you can take that complicated formula in terms of the Weierstrass invariants, stick those in, do the large mass expansion. That's what they did.
And then the second question is, the Seiberg classes remind me of photomorphism intersection theory. And I was wondering if when you're looking at these intersections in moduli spaces to cohomology classes, if there's ever a sense in which you need some more sophisticated intersection theory. Like
That's a great question. I don't know. That's really a question for Goethe and Kuhl. So they're looking at the case of algebraic surfaces. And the way they arrive at their conjectures is they use a lot of enumerative algebraic geometry. And I don't know more about what, so that's really a question about what techniques they use. It's a good question. I don't know the answer.
So, for example, when you try to consider invariants over families, there the context in which the difference between ordinary intersection theory and photomorphism becomes apparent is when this family is singularized, so you have some degenerate behavior.
Yeah.
Is this ever the case, or the family is not coordinated to give it to? Is there?
Well, no. The families of 40 theories that the sense in which I'm talking about families is over the U plane, or as I vary masses and numbers.
Yeah.
That's different from taking families format.
Yeah, I mentioned the later case. Where you have.
Well, here in parts 1 through 6 of the talk, we have a fixed four-manifold.
Okay.
It's only in the last part where we talk about coupling the supergravity that we start taking families of format. And there we weren't particularly looking at the algebraic geometry, we were just taking families of all. Yeah.
For the conjecture, it makes sense to go one dimension lower, right? To think about three manifolds, but then probably you get something like flat connections and Casson invariant contribution.
Oh,
on one side.
that sounds right. Yeah.
In Seiberg, that's probably more plausible to check. Because
Well, I mean,
it's
these
based
guys
on-
checked it. These guys checked it. I mean,
For three manifolds.
no. I mean, they checked. They reproduced the word, the conjectures of Goethe and Kuhl. I want to stress these are really complicated formulas. I mean, the check is amazing. What you're saying sounds exactly right. Mourinho and I actually did something like that with the standard SU2 and got connections to Seiberg-Witten and reinterpreted Meng-Taub's formulas and stuff like that.
Yeah, that's what that.
So, do you have a guess for what the sort of meaning of this Q is more categorically? What is the?
Well, I can tell you what it's, I mean, that's, I like the question because I was absolutely interested. I like the question because, I find it astonishing that we get these integral coefficients. One thing I can tell you that they are not is intersection numbers on the non-abelian monopole moduli space. Why not? Because I had to factor out all that other stuff. So that's what they are not. I don't know. I like to think that maybe they're deep categorification of some vector spaces, but I really don't know.
So for a given theory, this is really a series, right? There's, like, this is, you're listing some coefficients.
Yeah, yeah, I mean, for a given, so, for a given theory, so if you choose F, then you have a whole, so the theory is specified. Theory is specified by choosing F, the number of flavors, so 1, 2, 3. We love to do n if equals 4. Elias tells me that the computational complexity just absolutely explodes. Like F equals 1 is relative instantaneous, F equals 2. 3, the computer has to think a little bit. For F equals 4, for F equals 4, you can run it for hours and hours and hours and nothing happens. So, you know, superconformal. That's the superconformal one. And so for K3, with a lot of work, we got the answer for K3. So we actually know this Q for K3 for F equals 4. But and it's there, it's going to be some polynomial in the masses, which is spin 8 invariant. It's going to be written in terms of spin 8 invariance of the masses. And I would conjecture that you'll just see a J function. Just based on modular weights, and that would be an analog integrality, but that's really just a wild conjecture, because we have no data. Anyway, back to Osman's question. For F equals 1, 2, and 3, so you have QF, and then you have an infinite set of polynomials, where, you know, 1 for each point in this point.
You understand why the partition function even has that product form with Q in the numerator? It's added. Like that, yeah, that form of.
No.
Never mind what Q is, can you even tell the equal factors like that?
Let me go back. Looking at hundreds of examples shows that the sum is amazingly simple. No, there was the fact that this denominator is so simple is incredible. So
Must mean something.
I agree. I'm just reporting an experimental result.
Yeah, it's unbelievable.
Yeah.
Similar thing happened with amplitudes. Yeah. And look what happened.
You mean scattering amplitudes? Yeah, that's right. Yeah, so yeah, that might be a good analogy.
Do we have any more questions? Okay, let's think right here. So there's plans to go for dinner. We're going to the restaurant at 6 and we leave here at 5:45, right? Let me know if you want to join. We're going to the tennis place on that.
There's a talk at 3:30, but.
Yeah, no, there will be a talk at 3:30.